Okay, so we went through the theoretical understanding of median and medians. Again, it's a difficult algorithm to wrap your mind around the first time. So keeping that in mind, I actually wanted to go through an example of using the median and median algorithms, go through every step so that you understand how it works, and then we'll do a time analysis, and then we'll answer the big question, which is why do we break the lists up into groups of five? Okay, so for our example, we are going to just take a sample array, and I just chose an array from 0 to n minus 1, and here I am assuming 0 indexing. Okay, just for the sake of completeness, because I know most people are used to 0 indexing, so we're gonna go with that. To all you MATLAB people that do one indexing, MathWorks, you are wrong. That's the worst part about MATLAB. So 0 indexing is correct. So we're just going to assume that here. So we have an array that has all the elements from 0 to 19, and I scrambled them up. Okay? And let's say the point of this, let's say we want to find the median in this array. Now, I mean, the background I gave you basically means that the median of this array, by definition, has to be either 9 or 10. We're going to assume 10, right? Even elements of the array. So we're going to assume, so the median of this array is 10. And each of the elements of this array, the values are their ranks, right? So this is just for the sake of visual clarity. The values could be anything. But for the sake of visual clarity, we made the values their ranks. And so to find a median of this array, we will do linear time selection. We will do quick sort plus median of median. I mean, quick select plus median of medians. We will call this function, which I have named median of medians, and put the array as an input and give the rank of the element we want as rank 10. The element that's of rank 10, i.e. the element that's n over 2, that is the median. Okay? Okay. So what do we do with this array? What's the first step of this array? And the first thing we need to do is find a pivot, right? We need to find a pivot because that's how the selection algorithm works. We want to partition the array into 3 parts, i.e. the pivot, the part that's smaller than pivot, and the part that's larger than the pivot, right? So in order to find the pivot, we first need to reorganize the array into lists of 5. Okay, so this is the same array as before, 3, 2, 14, 14, 6, 0. We just arrange it 3, 2, 14, 6, 0 into lists of 5, into columns of 5, I should say. Okay, first we reorganize it, and then what we'll do, again, we're not actually doing this, but we need to find the median in each of these lists. Okay, so the median in this list is 3, right? And the median in this list, in the second column, is 12. Now, for the sake of visual clarity, we only need to do 7 comparisons to find the median. But for the sake of visual clarity, we are actually just going to sort the arrays. Okay, we'll say we're sorting the 5-element arrays. Again, sorting takes constant time too, so it shouldn't affect our runtime analysis. But sorting isn't a necessary step. We could stick to just finding the median, just selection. But visual clarity. This is a learning exercise. Okay, so we're sorting each of the 5-element columns, and then these elements here are the medians of each of the columns, right? So we still need to find the pivot to use on this entire thing. So the pivot will be the medians of these medians, right? So we look at these, so we take the medians and put them into a new array. And then we say we want to find the median of this, i.e. we want to find the element that is of rank k equals n over 2. In this array, n is equal to 4. The median's array, n is equal to 4. So we need to find the k that's of rank 2. And since this is 4 elements, since the original array was not very big, since the median array is very small, it's only 4 elements, this is smaller than our 5 elements base case. So we could just sort this in linear time. We'll just sort the medians in linear time and return, if we call this b, we return b of 2, which is equal to 12. Okay? So 12 is our new pivot. Okay? So what do we do with our new pivot? Well, we take it, and then we put all the elements, we go through the array and put all the elements smaller than 12 on the left side and all the elements that are larger than 12 on the right side. Okay? And so now we got a choice. We are trying, remember, we're trying to find the element that is of rank 10 in the original array. Okay? So we got 12 elements here, and then we got 7 elements here. Oh, not 7. No, yes, 7. Yep. We got 12 elements here, 7 elements here, and we got 1 element pivot. Okay? So the pivot itself is of rank 12. So that is not equal to k. So we can't return the pivot itself, right? So the pivot itself is not an element. But we know the element that is of rank 10 must be somewhere in this array. It must be somewhere here. Right? So what do we do with that information? Well, we simply recursively call median medians on the lower array for k equals 10. Okay, so we're no longer looking for, quote unquote, the median of this array. We're looking for the element that is of rank 10 of this array. Okay, and that's going to be somewhere in this area of the sorted list. Okay, so we now have a smaller array to select on. So what do? We do the same reorganization. We break the array up into 5 element columns, and then we sort each column so that we know what the median of each column is. Then we take this median, this list of medians, and we find the median of this medians. Since n is equal to 3 here, then we want to find n over 2, which is equal to 1.5. But of course, we have to feed in integers into functions. So we'll just take the floor of this, which is equal to 1. Okay? And so we could sort this array in linear time. We get 3, 5, 9. And so we do this. We get 3, 5, 9, and we return b of 1, which is equal to 5. Okay? So 5 is our new pivot. 5 is the pivot of this entire array here. Okay? So we do the same thing that we did before. We take the pivot 5, we take it, and then we put all the elements that are smaller than 5 on one side and all the elements that are larger than 5 on the other. Okay? So the amazing thing here is that this is already sorted, but it doesn't always have to be sorted here. It just happened in the original array that these numbers were already sorted. Anyway, so we have 2 arrays. We have the elements that are smaller than 5. We have a lower, and that is 5 elements big. We have the pivot itself, that is of rank 6, that of rank 5, and we have the a upper, the elements that are larger than a pivot. And there are 6 elements here. Okay, so we are looking for the element of rank 10. Okay, so what do we know? We know that the pivot itself is of rank 5, so that doesn't help us. We can't return the pivot. Okay, so that we're not going to return that. So we know that these elements are of rank 0 to 4. So we can't return and we can't recursively call on this array. Instead, we must recursively select on this array, right? We know that the element of rank 10 must be somewhere in this vicinity, okay? So we make the median and medians call on A upper. But wait, here's the key. A upper if we look for if we just pass in k into this function, we're looking for the element of rank 10. I mean, this A upper is only 6 elements long, right? The thing is, when we're dropping these elements, these 6 elements here, when we're dropping this, then the 10th element of this entire array would be the 4th element of the rank 4 element of A upper. Okay, so we just calculate that as k. Oops. We just calculate that as k minus the size of A lower plus 1. And this plus 1 is simply to account for the pivot. This plus 1 is simply to account for the pivot. Yep. Here. Okay, size of A lower is 5. Size of A upper is 1. And this pivot is simply to account for this A lower, and this plus 1 is simply to account for the pivot, and it's simply to account for the fact that we're doing 0 indexing. Okay, so we're getting rid of these elements here. We're getting rid of 6 elements that are smaller than the element of rank 10 in the original array. So now we're simply looking for the element that is 10 minus 6, the element that's of rank 4. Okay, okay, so now we got to recurse on A upper. So we do the same thing again. Again, we're close, but we're not at the base case. Remember, the base case is if we get an array of 5 elements, then we could find the median or find any rank in constant time. We just sort the array and just find any rank in constant time. Okay? But if the array is larger than 5 elements, we got to recursively call the median of medians algorithm. Okay? So this array is unfortunately larger than 5 elements. It's 6 elements, so we have to go through this song and dance again. We break this array up into columns of 5, and in this case we only have one column of 5 and another column of 1 because there's only 6 elements. And then we need to sort each column. It was already sorted, great. And now we have an array of medians. And then we could call median of medians on the array of medians. We want the median of this array. So since n is equal to 2, n is equal to 2, and the median is n over 2, then we get 1. So we want the rank 1 element of B. Okay, and in this case, the rank 1 element, B of 1, is simply equal to 11, right? And 11 is our new pivot. Okay, the end is a little exhausting, but stick with me. So 11 is our new pivot. So we make 11, we bring 11 to our pivot, and we put all the elements that are smaller than 11 on one side, and all the elements that are larger than 11 on the other. In this case, there's only elements that are smaller than 11. So A lower is size 5, and A upper is of size 0, and we want the K that is the pivot. That is, we want the element of rank 4. Okay, and actually pivot is of rank 5. Yes, that's correct. So we can't return this pivot because the pivot is of rank 5 and we want the element of rank 4. It's so close, but we can't return this element. So now we got to recurse on the lower array. Okay, we got to call median of medians on the lower array, and in order to do that, we got to call median of medians on A lower, and we pass in K, which is 4. K. Okay, and again, this would simply be 6, 8, 9, 7, 10, and this is 4. Okay, so we recursively call median and medians, and finally we're at the end where we say, hey, look at this. This array is smaller than smaller than 5 is less than or equal to 5 elements long, right? So we can sort it in linear time, and when we sort it in linear time, there, bam, we could get the element that is of rank 4 by a simple lookup. And we get the element that is 10. We get the element 10. Okay, so remember, in the original, we wanted the median of the array. From the very beginning, we knew that the median of this test array is of size, it is the element 10. And so we did all this rigmarole and we ended up with 10. So it proves the algorithm works, right? The algorithm works, at least on this example. And in general, it does work. Or as long as your logic is sound, the algorithm should work regardless of the example. Okay, and so you could write this out, and this is the algorithm. The median is algorithm written in a C-like language. It's not perfect C because of course you're missing semicolons, and you're doing stuff that you could really only do in Python. But it is rough. This is approximately C, or Python. It's also Python. Okay. It's pseudocode. Let's just leave it at that. It is pseudocode. Okay, so the question here, the question is, how long does this array take? I mean, how long does this procedure, does this algorithm take? Okay, so breaking the sublists up. So breaking the sublists up into lists of 5, this takes some constant time. Okay, I know some of you may be saying that it takes O of n time to break it up. That might be true if you're allocating a new array or a new memory elements and putting the sublist into new memory elements. But in general, all you really have to do is change the indexing scheme and leave the elements where they are. And to do that, I mean, it should only take constant time if you're clever, if you're efficient, I should say. Just because you don't come up with the most efficient answer doesn't mean you're not clever. Okay, so sorry for that. Anyway, so creating the sublist takes some constant time. Finding the medians for each sublist. Finding the medians. Okay, so you got to go through each sublist, each chunk of 5, and find the median. Okay, so how long does this take? Well, the sorted on lengths of 5 takes some O of 5 constant times O of n over 5 sublists. Right? So this procedure takes O of n time. Okay? So in the base case, if we have the base case, we simply remember we just saw the base case. The base case takes pretty much constant time, or it takes sorted time. So this takes, you know, O of 5 time, less than O of 5 time. So, and I should say 5k time. So this takes constant time. But we have this. Okay, so if either finding the median and medians takes constant time, or finding the median and medians is a recursive call. So how do we handle a recursive call? Well, we say that the original algorithm, the top case, takes t of n time, and the recursive call finding this median and medians takes t of n over 5 times, because you have n over 5 medians. So in order to find the median and medians, you recursively call the median and medians on just the median array, just B, to find the pivot, right? So this procedure takes t of n over 5 time. And finally, we have a recursive call. We have a recursive call. So remember, if our pivot is poor, like, things could go bad, but this medians pivot means that it is at least greater than or smaller than 3 out of 10 elements, right? So every time you do the partition step, you are chucking 3/10 of the array, right? And the maximum size of the array you could be left with is 7/10 of the array. So this step takes t of 7/10 n. Okay, so the total recurrence together is t of n is equal to t of 1/5 n plus t of 7/10 n plus c of n. And so How long does this recurrence take? Well, again, we could do the recursion tree. We have n, we go to 1/5 n, we go to 7/10 n. The work here is O of n. The work here is O of 1/5 n plus O of 7/10 n, which is equal to O of 9/10 n, right? And then we saw at the next level, it was O of 9/10 squared n, and so on, right? So because this is a geometric series, we know that the work on each level is rapidly decreasing. So we got n plus 9/10 n plus what is it? 9/10 squared n plus 9/10 cubed n dot dot dot. And what's the solution to this geometric series? It's simply O of n squared. No, this is simply O of n. Some constant times n. Okay, so this is simply equal to some constant times n. So this whole thing becomes O of n time. Sorry, O of n time. Okay, so that is the median of medians algorithm, again, by example. Okay, so you learned about it theoretically. You learned how it works doing an actual example. So the last question I want to pose to you guys is that in the previous lecture or previous video, in this case, we'll just put that in the previous recording, we chose list of 5. Okay, so why did we choose list of 5? Why not choose list of 3? Why not choose list of 3? Surely the time it takes to sort or to select the median from 3 elements is smaller than the time it takes to sort or select the median for 5 elements, right? So why not make the lists, make the columns even smaller? So let's do it out. Let's do that analysis that we did in PowerPoint for lists of 3 and see how well the pivot performs. Let's say we have a pivot and we organize it into lists of 3. Okay. And when we get the median of medians, which is here, so we know that the median of medians is larger than these elements here. Okay, so the pivot is larger than, what is this? This is 2/3 times 1/2. So this would be 2/6 n. Okay, which is equal to 1/3 n. Okay, so the pivot has to be larger than 1/3 n. So in this case, we know that this term here, instead of 1/3 n, instead of 7/10 n, it becomes 2/3 n. Because again, as we showed here, at every partition, we are getting rid of 1/3 n elements. Okay, that's pretty solid. Okay, so let's write this out. T of n. So the new partition is at most 2/3 n large. That's a recursive call. We still do O of n work. Now, what is the time it takes to find the median of medians? How many medians are there? Well, there are 1/3 n medians, right? These right here are all the medians. Okay? So, what is the solution for this recurrence? Well, we could look at the recursion tree. We have n, so we go to 1/3 n. We go to 2/3 n. Then we do the same thing. 2/9 n, 1/9 n, 2/9 n, and 4/9 n. 4/9 n, dot, 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 dot. Okay, so the amount of work on this level is O of n. The amount of work on this level is O of 1/3 n plus O of 2/3 n, which is still equal to O of n work. The amount of work here is O of 1/9 n plus O of 2/9 n plus O of 2/9 n plus O of 4/9 n, which is still equal to O of n work. Okay, so the trick here is that the amount of work, the change here is that the amount of work on every level stays the same. So we do a simple analysis. We have O of n work at every level times the number of levels, which is log n levels. So we get this, T of n is equal to O of n log n, which is significantly larger than simply O of n. Okay, so if you make the list too small, the running time of the algorithm actually increases. And you can verify this when you actually, if you actually code this up. That if you code this up in a list of 3 instead of list of 5, the running time does increase much faster than the list of 5 case. Okay? So we can't make the lists any smaller. Okay, someone is going to point out, what if we make the list a size 4? Well, if you make the list a size 4, you're adding a whole bunch of complexities because the median is no longer a particular element, or the median is like, you know, more weighted towards right than to the left. So let's ignore the even numbers. It doesn't change anything. It doesn't change the math, the calculation, and you could do it yourself. But the point is that the smallest list, the smallest list size you can have, while keeping that linear time selection, that linear time running time, is 5. Okay? Okay. So why not make the list bigger? If we make the list bigger, in theory, we could get rid of more of the elements at every partition, right? So let's see. Why not make the list bigger? And again, instead of making the list size 5, let's make the list a size 7. So let's draw this out. 1, 2, 3, 4, 5, 6, 7. And I'm going to be a little smart here. I am using a iPad, so I could use the copy and paste. Copy, paste. Copy, paste. There we go. No, I only wanted 3. Oh, that's okay. 1, 2, 3, 4, 5, 6, 7. Okay, so the median of medians would be right there. Okay, so what is this pivot? How many elements are we guaranteed to get rid of when we have a pivot, when we select a pivot like so from a list of size 7? Well, again, let's draw it out. Let's analyze it. The pivot, the median of medians, is larger than this many elements. That's good. So let's see this. Let's get this pen. That's 1/2 of the columns. This is 4/7 of the rows. So T of n, we could write this out, T of n is equal to something. Is equal to the number of medians, which is t of 1/7 n, the number of medians, plus t of 1 minus 4/14, which is 10/14. Yeah, there we go. 10/14. Okay. 10/14 n plus O of n. Okay? Not too shabby, actually. Because, this is, again, as we said, we are dropping a significant number of elements at every partition. So, that's pretty good. And in fact, if we do the recursion tree out, n 1/7 n 10/14 n, we get O of n work. We get O of 1/7 plus 10/14 n work, which is equal to O of 12/14 n. Then at the next level, we're just going to have even less, 12/14 squared n work. So we still get that same geometric series, and we still end up with a linear running time. Okay, so list of size 7 does work. All right, list of size 9 would work too. List of size 101 would also work. So why don't we use that? Why don't we use list of size 101? And the crucial thing to note is that we're still doing some work here. This sorted is still some constant amount of work. So again, this is one of those things where theory and practicality have to go hand in hand, right? In theory, the running time is the same, whether or not the lists are of size 7 or 9 or 100 or 5. In theory, the running time is the same. The O notation is the same. But in practice, if you're manually sorting lists of size 101, if that's your base case, it's going to be way slower than sorting lists of size 5, right? So the O notation here omits the constant. And while eventually this n becomes way more important than any constants, in practice, constants still matter, right? It matters if something takes 2 days versus 1 day, right? It matters if a program takes 2 hours versus 1 hour. So it matters that even if the scaling constant, even if the constant scaling factor isn't evident here, it still does matter. Okay, that constant scaling factor, and it becomes relevant when you're comparing two algorithms that have the same running time scale, that have the same running time speed up. Okay, so when two algorithms both have linear running time, then the constant before that linear running time becomes more relevant. And that's why we want to choose the smallest list possible to save on the sort of manual sorting we have to do within the algorithm. But the list has to be, the number of elements has to be large enough so that we maintain a constant running time. Okay, so that's why 5 works, so that's why we choose lists of size 5 instead of lists of size 3, instead of lists of size 7. 5 is that sweet spot for median and medians. Okay, so now that I've beat this horse to death, I hope all of you are now experts on median and medians. And yeah, hopefully we could discuss some more divide and conquer algorithms soon.